Good morning, good afternoon, good evening, all the Digital Future participants. Welcome back. Today, it's a great honor for us to invite Philippe, who is important figures in the world, and it's a great honor for us to have him here. In the past few days, in the past 4 days, we organized a special topic on the performance-based digital design methodology, which is part of the Digital Consortium PhD courses and PhD platform. So you and me is trying to establish a platform for the global PhD students and will give opportunities to different continent students have the special chances to learning from the best scholars from the world. So although we have some normal courses in our every school, universities, we try to set up some different credits. Maybe, for example, in Tongji, you have 2 credits to invite these prominent, important professors to give lectures. So, which is like a brief introduction for the students, especially the year 1 PhD candidates. They will understand what's happening globally, and they will help them to make decision to set up their own research topic in the future. And for the past 4 days, we have some female lecturer like Jenny Sabin, Areti Marco Polo, and we will have Meta as well. And also we have Achim, Roland, Machia. They're all the best scholars from the world. So today is a great honor because we all know Philippe is really special. He is a full professor at Institute of Technology in Architecture at ETH Zurich, where he also leads the Block research group with Tom Wamel. And he is right now the director of Swiss National Center of Competence in Research, NCCR, in digital fabrication. He applies research into practice on the design, engineering, and construction of novel shell structures, and who is also the recipient of numerous awards, including the Rosler Prize for most promising young professor from ETH Zurich in 2018, and the Berlin Art Prize 2018 for Bankunst. He actually participated. He was invited to participate in Venice Biennale several times, and this year he's also making a pavilion. We're all looking forward to see what's happened, and that is should be a very important pavilion this year in the world. So we would like to give the screen to Philippe. We're looking forward to the great lecture tonight. Thank you.
Thank you, Philippe. Thanks for the invitation first and foremost, but also for this very kind introduction. Here we go. I think you should be able to see my screen now.
Yes.
It's my pleasure to indeed be invited again to this to Digital Futures and to this PhD program. It's my pleasure to share our research, but also I try to sneak in as many updates as possible, because I'm also, of course, aware that this is not the first time that I present here. So I hope that you will learn some new things or get some updates on some of our projects indeed. So I titled my lecture Sustainable Digital Concrete Construction. I do this on purpose to maybe immediately set the tone about, for me, the target is sustainability. The way that we achieve it is through computation. And a material that we are exploring currently is concrete, which is being labeled as the most destructive material on the planet. And so I hope that through my presentation, you will see that my title is not just a provocation, it's also not kind of a weird or confusing or misleading statement, but that hopefully through going through the process, how we actually approach structures, that you will see that even a material like concrete, when used appropriately, indeed can be quite disruptive and even challenge many other materials when it comes to environmental targets and so on. So with that, I think I already set the stage right. I also hope that I am preaching to the choir by showing a slide like this. I nonetheless still present it because I believe this should be driving much of what we do in the fields of architecture, engineering, fabrication, construction, because on a global level, and of course these are rounded up numbers, it's some estimations say 36%, other 39%. It depends also which target that you're looking at. But this is easy to remember. As an industry, and I'm talking about building, construction, operation of buildings, and so on. So everything that has to do with our business, on a global level, we are responsible to 40% of the impact, which is something that I think we need to absolutely take serious. So 40% of the global greenhouse gas, man-made greenhouse gas emissions come from construction and buildings. 40% of resource consumption, and what's of course problematic is that this is referring to virgin materials, so for first-time resources. 40% of global waste production. Again, this is mind-boggling that this is happening. And then also this you might have heard for sure, that a lot of energy is being used both in the production but also in the operation of buildings indeed. Again, apologies if all of this is known to you and if I'm repeating myself, but if we were to build like we build today, in order to provide an average quality of living to all these people, these 20% more people that are expected to be on this planet in the next 20, 30 years, then this is what it translates to. The challenge that we have ahead of us is we need to build the equivalent of 1 New York City every month for the next 40 years. So we shouldn't do this as we do it now, because these gigantic global numbers still this that argues this is probably something, this framing was very similar in other lectures, but I want to just emphasize that those are indeed the two aspects that I believe we need to fundamentally disrupt and find other solutions for. We need to design, we need to build differently. As a half architect, half structural engineer, I would call myself a structural designer or an architectural designer. An architectural engineer, that is. I will be focusing mainly on the embodied emissions, so the ones that are related to production of materials, construction, and so on, and less the operational energy. But just a quick statement there. Theoretically, the world would have a very straightforward solution to reduce the operational energy and emissions very directly, by actually switching to renewable, greener sources, green sources of energy. But we don't have an as straightforward solution to a problematic embodied emissions. I like to adopt or borrow this equation by Catherine de Wolf, which she developed for her PhD with John Oxendorf at MIT, where she really brings or reduces the complexity to what really matters. The global warming potential, which is a bad thing. So it's basically the amount of pollution associated with a building, a construction, can be just the sum of all the part of this building. And then there's two things that are important. What she calls the structural material quantities. So basically the volume of material that one uses. And then the second is this ECC, which is the embodied carbon coefficient. These are basically coefficients that describe or that capture the pollution associated to a material. So you see in this equation that actually our target should be very simple. You can either make a structure, so reduce the volume significantly, a structure very light, or you can use very low impact, so low pollution materials. Ideally, of course, you achieve the two. But so maybe an important point to make here is that in engineering history, the last decades, engineers have been mainly focusing on always lighter, lighter, lighter is better. But this is not necessarily true, right? Because if you make it lighter, but then in exchange, you use a highly polluting material, so a material with a high embodied carbon coefficient, like carbon fiber, for example, then you might be offsetting many of the things that you're trying to achieve by going lighter. So what I will show in this lecture is I will talk about strength through geometry. I will explicitly also talk about material effectiveness. Again, I already made this comment just now. It's not just about efficiency in the traditional way of defining it, so in being less material lighter, but it's more about how you use material. So this is key. And then, of course, as I already said all the way in the beginning, we use computation both for the design and fabrication to try to design and build indeed differently. So right now, we are about 12 years into our adventure. So I started my chair in August 2009, and we have tried to not just remain theoretical, not just stick to the design on the design side, but also then question how we build things. And now increasingly, we're trying to translate these ideas in real projects, which really is a totally different kind of challenge. And I will give some insights on this later on as well. Let's first maybe look at computational fabrication. I, on purpose, don't call it digital fabrication because everything is digital. A simple CNC mill is also digital. I call it computational. And what I mean by that is that we don't just do things digitally, but in the design process, we already start to encode fabrication logics, fabrication principles, fabrication opportunities, but also limitations, so that you can really capitalize on those advantages. So an important strand of research that we have undertaken or important to us, that is, in our last kind of years, is to address the shaping of these structural geometries, these shells, which are non-standard geometries, and to try to address the huge waste and cost and also logistical kind of challenges associated to realizing structural geometry. Also the single use of formworks and so on. In that strain of research, we have been exploring the potential opportunities of flexible formworks. So here, this caricature, this kind of diagram quite clearly shows what we're trying to achieve is that if you would use a traditional formwork to realize these non-standard geometries, then you need quite a lot of material that will be single use, a lot of scaffolding, a lot of foundation to hold all of this up. And so in a way, what you see on the left, the traditional rigid formwork is basically a very brute force approach. While if you introduce flexible formworks, you can go very light, but that also means, and this relates to my comment about computational fabrication, is that you then need to take the restraints and the equilibrium and the structural logic of these flexible formworks, you need to take it into your design framework. So a prototype of these kind of ideas we built in I don't remember, in 2017, 2018. Sorry that I'm blanking on this now for the moment. But this is, of course, the work of Mariana Popescu. Here you see basically that if you get the geometry of your formwork right, so if you actually use structural geometry for your formwork itself, that you can use literally something as simple as a stiffened sweater to build, for example, a concrete shell. So here a summary of some of the steps. So this is using 3D knitting that is super lightweight, easily shipped just in 2 suitcases in this case. And then with these technical textiles, these 3D knits, you can also create all kinds of pockets and to include other kind of features and so on. Maybe some key messages here is that we develop these systems also thinking what happens on site. So for example, this 2-layer fabric basically has all the clues, all the connectivities, all the slots, all the components are included in order to be able, even with workers that we didn't meet before, to do this, to realize this complex geometry very smoothly and easily. In this specific project called Knit Candela, we also wanted to express another materiality. So the inside of the shell, the formwork was, so the fabric was left in place to have this kind of unique aesthetic. But why we did this project was that behind this colorful intradust layer, there was actually quite a sophisticated lightweight shell with stiffness in 2 directions. A sophisticated shape that could be easily realized by this double layered knit where little balloons were inserted in order to create these pockets at the end of the structure. Most important for me, though, is increasingly to always be very clear why we do demonstrators, what we want to achieve in our prototypes, and exactly also then to try to check with the actual numbers and statistics if we achieved what we were trying to set out. And so that is why this slide to me is maybe most important, is to really kind of double check, like, did we achieve what we set out? So what we try to set out here is to actually achieve this in a very tight schedule, only 3.5 months from a first invitation to realization. Of course, in a Chinese context, this is extremely slow, but nonetheless, I have the feeling that we achieved quite a bit because this 3.5 months included design, many engineering iterations, developing, so prototyping the formwork system almost from scratch. And then, of course, including also the fabrication, which took only 36 hours to knit the entire formwork. This formwork weighed only 25 kilograms. The formwork, so not including the reusable external kind of props and things like that, but the cable net and the knits and all connectors cost 2,300 euros, which is very little. And the shell weighed 5 tons for 50 square meters of concrete. So this is what we wanted to challenge ourselves, is that can we indeed live up the promise to have for a sophisticated structure, a simple way of going on site and to reduce the waste and things associated to these non-standard formats. We're lucky that and this is a project that has been going on for much longer, but that we can also translate these ideas not just in prototypes, but also for real buildings. This was still the prototype for this, where we indeed use a similar idea of a lightweight cable net formwork with a woven textile kind of draped over it. So in this case, what's perhaps interesting to point out is that the system that we developed with these cable links could be entirely taken apart and reused. And indeed, 85% of all these components were reused in the final project, even though the shell received quite a lot of updates compared to this prototype. This prototype in 2017 was extremely important in the sense that we indeed learned a lot, but more importantly, this prototype every single step was done with the industry partners that would realize the real project. And this was key because it allowed us really to together figure out what the real bottlenecks were, and then also to build up confidence that, to translate such an extreme innovation a tension flexible formwork at quite a large scale. So what you're looking at here is roughly 20 meters by 10 meters by 7.5 meters in height. So this is a large surface that is being built on this flexible formwork. So this is for a unit on a building that we're building. It's called Hilo. For the roof, this now finally got built. So here you see a little video with some hints of the final double layer shell being built. This was after decentering. So here you see a slight reconfigured kind of formwork that could be easily put together and assembled on site with all the connectors and also elements to measure the geometry so that it's exactly where it needs to be and so on. So here you see our team, the BRG, who are not just computational experts, but also fabrication contractors or formwork contractors, it seems. It's a 2-layer shell. So it actually has 2 very thin layers of just a few centimeters that are connected with stiffeners in between the insulation blocks. And so this was then the project as built on the for the Hilo unit. This is on the Nest building, and I show you some more recent pictures just to all this unevenness. These pictures were taken directly after decentering, so you see actually that now after a few months later that these uneven spots really blend out, and that this linear surface is really starting to look very unique and clean. Of course, then also, it's not just about the shell, it's a real project. So here the different rooms have been installed. These are very simple prefabricated timber boxes. So the project finally, it's opening, by the way, in October. So look out for the press release and the launch on October 6th, I believe, or October 8th. The unit will be inaugurated. It is really a project indeed. So here you see the facade elements coming in. So it's exciting for us to see that this project that started, can you believe it, in 2011, that we have been working on and trying to convince all kinds of authorities, clients, funding, and so it will be quite a celebration that after almost 10 years, this project will be realized and inaugurated this year. Maybe for us, the biggest achievement in this project is that it was particularly the roof was developed extremely consistently through this open source computational framework, which is called Compass. It's a framework, a Python-based framework for collaboration and exchange, mainly in research, but we see this as a very valuable kind of model to start to have a much more integrated design to engineering, to fabrication, to all the way to construction. And even if you plan for it, for demolition and deconstruction at the end. So we use Compass as a hub between all these different partners, some of them with absolutely no computational background. So it allowed us really to have a clean, trustworthy, central hub that generated all the information, but that also allowed us to integrate very new research ideas in a real project with real expectations, budgets, timelines, and so on. So in a way, this allowed us to try a different kind of more integrated project delivery model where we have a central kind of computational hub. And from that, as I already mentioned, all the different information without any data loss, something that would not be possible with a typical BIM approach, without any data loss between all the different partners, because it's all generated from the same lightweight data structures and geometrical models. Okay, but so a key message for us and that I want to share is, of course, strength through geometry. So this has to do with structural geometry, particularly with reintroducing these elegant structural forms from the past. More specifically, And you will understand, and I will explain all the layers why we're reintroducing compression-only geometries like these beautiful vaulted shells. In fact, the most active and the largest part of our research group is actually our subgroup on masonry structures. And this is also what I did my PhD on at MIT. I developed methods to assess the stability and the safety of historic structures. And that is something that we are now going back to, because it's also an extremely big challenge to, in a respectful way, to treat our architectural heritage. But it's not only about preservation. We can also really learn something from this elegance and this restraint that these master builders had, and that is why we developed tools like Rhino Vault. This was initially developed by Matthias Rippmann, that allows us to translate these ideas and to now also start to shape structures that don't need any reinforcement or other, and that can just stand, for example, in compression only, like this armadillo vault that we built at the 2016 Venice Biennale. That was dry assembled, just stone touching, geometry keeping it together. Strength through geometry is not just about fancy shapes and so on, but this project in South Africa that I was lucky to be part of in 2008 is really the one that to me really clarifies why I insist that we should reintroduce these funicular geometries. And it has to do with the ability of compression vaults and shells and arches to not only significantly reduce the amount of volume that you need, but also the stresses in the material are very low. And so for those of you who don't understand stresses or don't have an engineering background, it means that what the material needs to provide, the strength of the material can be extremely low. And that means that the pollution of a material which is almost one-to-one proportional to the strength of that material. So ultra high performance concrete is much, much more polluting than low strength concrete, is much, much more polluting than soil concrete, is much, much more polluting than pressed soil tiles, as you see here, and so on. So here what you're looking at is why I show you these two images, is on the right, you see these very thin tiles that had to be carried in very small packages because this material is so weak that you can just break it in your hands. But on the left, you see that if you place this material where the forces want to go in compression, then this becomes a totally safe structure, even with such weak materials in bending, but you activate it in compression. So these arches that are good for certain loading cases, you need to find also ways to stiffen them, which means to provide solutions for live load cases. This you can do by adding stiffeners, or what I showed you in this vault, this stone vault in Venice, the armadillo vault, we used positive double curvature, but you don't always have the structural depth to achieve this double curvature. So adding stiffeners is also a very effective way. And then by adding a tension tie, then what we just did is we provided an alternative for a beam or a floor plate that is 70% lighter. So I'm not talking about crazy computational kind of strategies. I'm just talking about reintroducing these structural principles that have been abandoned about 50, maximum 100 years ago. What a pity that we no longer use these arches. And I would say the missed opportunity is indeed all of this material saving that we get for free. So initially we did this to address these problematic situations of this low-cost housing, so-called low-cost housing. By mimicking how we built, this was really not an appropriate model for example, an African context. So let's now shift to material effectiveness, and I will show this in a context of, also in our context, we need to build a lot of these floors. So if you look at a medium high rise of 10 10 stories, so 10 floors and higher, then you will see that 3/4 of the weight of that building is actually in the structure. So again, and sorry if this sounds like repetition, but if it is, then please now remember it forever, because this to me was absolutely crazy to learn, that 3/4 of the weight of the building is there to keep itself up more than anything else. And then when you zoom in a bit more, then we see that more than half of that weight is in spanning space, so it's basically in the floors. Most of these floors are in reinforced concrete, so that is a lot of material, that is a lot of pollution, that is really actually one of these key bottlenecks that we should disrupt. Probably this was part of Achimenge's presentation as well, because I learned this number from him, that globally in the next 30 to 40 years, another translation of this 1 New York City per month to be built is that we will need about 300 billion square meters of floor area more on this planet. So that is how many square meters of floor need to be built. So the image in the back, considering that of all these projects, 40% of the material used is basically in the floors, can we do this better, right? So this is one of these key polluters that we need to do better. I already talked about this, that concrete is labeled as this most destructive material on Earth. That is absolutely correct, but it is also related to how we use concrete. And I will make it very clear that reinforced concrete, plates, beams, and so on is absolutely not how this material wants to be used. And there's some very good hints for this. Here, this is a graph done by the famous University of Cambridge material scientist, Mike Ashby, where he plots on a logarithmic. So here in the vertical axis, you see it, oops, it's a logarithmic scale. So this is non-linear, right? This is exponential. You look at the embodied energy. And of course, what's important is embodied energy per unit mass. And you see that cement is actually down here, and other things like aluminum, metals, and even the woods are on a several level of cement. But you see that concrete is all the way here on the bottom, right? And what's actually, this is a bit curious. So why is it then that concrete is so polluting? It's maybe not about energy, as I said in the beginning, but maybe more about emissions. And there you see something similar happening. So other materials that we use, here is steel, right? Copper and so on. We see the cement here, but concrete is equivalent to straw, stone, things like that. By the way, here look at fiberglass, and carbon fiber would be with 16 all the way on the right of the scheme. By the way, aluminum extremely polluting, extremely carbon intensive. Of course, the only material that we cannot beat is sustainably sourced timber. But I want to maybe make one comment about that, is that this carbon negativity, so this locking in carbon, and the rationale there is that trees are basically absorbing carbon throughout their lifetime. Is what's really important there to know is the end of life scenario of these timbers. Because if they rot or if they are burned at the end of their lifetime, then all this carbon is released into the atmosphere again. And so that means that you don't have any of these negative benefits. Another maybe comment to make, and this is not a statement about timber. Timber is an amazing material that we need to design with as much as possible, but how much sustainable sourcing can we do? Because the challenge is gigantic. And that is why, if you take anything away from my lecture today, is that I would want our discipline to be less black and white, less kind of this is good and this is bad, this is green, this is not green. We need so many solutions, and it's not black and white, because actually how we are using concrete, it is probably one of the solutions of the many solutions that we need. So, okay, sorry, I'm digressing a little bit here, but so what is then my message here is that concrete seems to be not that bad at all. But what is then the hint is that we should maybe use concrete how it wants to be used. Concrete can be seen as an artificial hybrid kind of stone. So let's use it how a stone wants to be used in compression, as a vault, as an arch. And indeed, we already looked at this compared to the reinforced concrete beam, which is actually flawed from the beginning, because in order to activate the reinforcement, the concrete needs to crack, which means that water can infiltrate, which means that the structure will have to be replaced after 40, 50 years if it's outside, and. So by reintroducing the stiffened tight arch, we just get already for free this 70%. That is where we started to then see, like, can we go beyond this simple diagram, and can we start to really also produce three-dimensional floor plates that have these properties? These are some of the early prototypes where you see the shell. So the shell is basically to take the self-weight of the construction, while the stiffeners are there to take the live loads to the corners. Very early on, we tried to also immediately address bespokeness and also the fabrication challenges. So this is a sand 3D printed floor, very weak material, but we demonstrate that these floors with equally weak properties as the materials that I've shown in South Africa can take actually all required building codes. Here, of course, we are crushing it to failure to really understand the ultimate capacity of the structural elements. And this is, everyone loves this kind of load test. This is 1.2 tons of ETH nerds. This was half of our group at the time, standing on this very thin 2 centimeter unreinforced shell. So just to clarify again, is why are we doing this? With the backdrop of 40% of all these kind of medium high rises that are populating, that are basically being built in all these growing urban centers throughout the world, we now have a solution that uses 1/3 of the volume of concrete, only 1/10 of steel compared to the reinforcement in the typical floor slabs. This translates to a fraction of the embodied carbon associated to these floors. We also are developing those as dry assembled prefab, which is a very important aspect to also capitalize or to be able to make this system feasible or challenging the status quo. We are really pushing for prefab so that we can have fast, precise erection on site. Because the stresses are so low in the material, we are actually allowed to use other materials, so low strength materials, a lot of recycled content. And because we separate compression and tension, these elements, if not reused, then they can be very easily recycled because there is no pollution of materials, there's no embedding of reinforcement and so on. So this discreteness is a big opportunity, and I will give you just one hint that this is really starting now to be implemented. Also these cavities, by the way, all the stiffeners, we just need the structural depth, but we can start to embed building systems so they don't have to be solid. And this is a huge opportunity because where structure used to be, we can now have very efficient building systems integration. As I already mentioned, but just to clarify what I was talking about is that we don't have this, so we don't have a structure that is very expensive and energy intensive to actually take apart. And here in these kind of things, it's just immediately given up to do recycling. So we don't have this because of clean separation. Maybe some of you were thinking that these floor plates look like Pierluigi Nervi's floor plates. Of course, everything we do is inspired by the past, but I want to emphasize a very big difference is that what you're looking at here is that these are still beams that are aligned very efficiently. This is fundamentally different than what I have been talking about. So if you don't have a stiff funicular shell in compression and you still use beam action, then you still have, because of this bending moment, you still have stress concentrations, meaning that you still need to use high strength, hence higher polluting materials. And so what we are showing with these extremely low stresses in the material, that opens up the opportunity to activate these new types of materials that are made from industrial waste on the left, or excavation soil on the right. And an example for that is my colleague Benjamin Dillenberger at DBT in the Digital Building Technologies group at ETH. He's now really developing also binder jet prints that allow very precise structural components to be printed here, for example, from 100% demolition waste. Okay, so I already talked about this unit high-low. So what's neat is that the very first real scale, because we're talking about more than 5 by 5 meters, unreinforced funicular floor has been built here in this unit. So here you see roughly the dimensions. For this, we made this formwork. This was our team that assembled this again. So our team, the formwork experts. In this case here, and this is maybe an interesting detail, is in order to make sure that the shell is activated from the beginning, we have some post-tensioning along the edges. So the tension ties are post-tensioning. And in this case also, you see that we have this integrated hydronics, which personally, I think it's not a good idea, but this was a collaboration, so we had to accept these kind of additions by our partners. Why I mentioned that this is, in my opinion, not a good idea is for the important target of actually keeping materials separate, so that they can be cleanly taken apart, that we can use them in after the end of life, that we have easy strategies for recycling and. So here you see some of the pumping. So very thin shell, just 3 centimeters of structural, then 2 centimeters of additional for embedding of the pipes, and then the stiffeners are only 2 centimeters. So this here you see after casting, we kept the foam blocks as stay in place to add insulation to make sure that the pipes radiate in the right direction and so on. After decentering, we had a little bit of an unpleasant surprise that there was not a perfect mixing of all chemicals. So now we have to find a way to deal with this. So beautiful, super clean. You don't see it in this picture because it's not a good quality picture, but the finish that could not have been perfect. So you can imagine how frustrated we are that the concrete experts managed to not mix the mix properly. So this is very frustrating, but we'll deal with it anyways. Okay, but so this all still is a bit of prototypes. I'll try to now sketch what this really could have as a global impact. For this, we prepared this case study of one of these very common traditional medium high rises, let's say 25 stories high, and we did the numbers. So on the left, you will always have the reference, which will be the flat slab, like how it is being built. By adding some post-tensioning, you can do significantly better. So for example, using hollow cores and things like that. The high-low floors is also in there as a reference because this is a really built project. So you see that in the high-low floors, we have half of the volume. This was, of course, because we had to make all kinds of compromises compared to what we know could structurally and work, because it was the very first time that such an unreinforced vaulted system was built. And then you see the outlet, the RFS. RFS stands for Ripman Floor System. So we have decided, and our partners have agreed to this, we are now commercializing these floor plates, and we want to call them after our late friend and colleague Matthias Ripman, because the beautiful 3D printed models that you saw earlier were actually one of the last projects that he really worked on. And so we found it appropriate to call this system after him. And hopefully this system will take over the world and be used for all construction. So this would be a nice homage to our late friend indeed. So, but as I said, the floors is one thing. On the global level of the building, this would translate to needing only 65%. But now when you again translate what that means for just one of these buildings, you remember the background image of all these buildings, this would translate in 7,500 cubic meters of concrete less. which, if you translate this into concrete trucks, would mean that you would need 1,200 concrete, so 1,200 concrete trucks less that need to go to this building site. This to me is absolutely mind-blowing. And we're talking just about one building, right? So this focusing on this one banal element that we all need the floor, this could be the impact. But maybe the impact becomes bigger when you actually look at the amount of steel. And you again look at the high-low floor as reference. So we need only 1/10 of the amount of steel, which would translate for this one building to 20 kilometers of 12 millimeter steel bars per floor. Or if you lay it out, it's all these reinforcements would take you from Zürich, where I live and work, to Brussels, where I'm from. So, but what really matters is actually not those volumes and so on, those are some nice statistics, but is indeed to start to translate this into the reductions in embodied emissions. And what's maybe important here is here on the right, you see this relation in, and this is again per unit mass, of the first value is the ECC, so the embodied carbon coefficient of concrete, versus recycled, so 100% recycled reinforcement steel, right? So if we would be using, virgin steel, then you can triple or quadruple this value even more, right? So this is, but you see the big difference between the impact of concrete versus the impact of reinforcement steel. And so that also means that to achieve this gigantic reduction per square meter here, you see actually that for this large volume reduction of concrete, we only, this attributes 40% towards that, while actually the taking out of the steel is maybe most important. So again, this relates to this material effectiveness, right? So you want to use materials how it wants to be used, how they want to be used, and also there place them there where they're most effectively indeed. So steel only as tension ties and concrete only as a vault or as a shell. Maybe an interesting anecdote is that almost all scrap metal in the world is being recycled to become reinforcement steel. So if we take out most of the reinforcement in all these floor plates, then we can use this recycled metal for basically functions, elements, components where it really matters, like for example, for long span structures and so on. And we would not need to go to virgin materials for these kind of components. So there could be a lot of side effects to this as well. Again, why we do this is that more than 40% of the weight of everything you see on this slide, all these buildings, is in the floor plate. This to me is crazy, and that is why we're pushing this. And I'm very proud that we got a very big partner, Holcim, to team up with us to now commercialize this to a real system. We're also pushing, so if you have ideas or real projects where you think this could be implemented, then let me know, contact me. We're very keen to collaborate. And I'll show you very quickly a real project that is now being submitted for building permit, where these floors for spans of 10 meters are being used in a real hybrid building, so hybrid office living, with also new ideas of super efficient building systems integration. So this is a super cool project because it pushes us to really confront ourselves with all the constraints of fire safety, acoustical performance, and assembly logic, cost of shipping, and so you will see this appear very soon indeed. Maybe one comment that I want to make is that much of this growth is not necessarily happening in my part of the world. So in developing Africa, there is a lot of building expected to happen. And then of course, Asia will still be quite high. And that is of course, India coming up and so on. So here I very proudly share a collaboration that we have with the Department of Environmental Affairs of the government of South Africa, where this image used to be a lake, but it's actually now dried up because these non-indigenous plants, so plants that were imported during colonial times, that are not adapted to the African kind of climate were imported, and they cause all kinds of problems. So already during Nelson Mandela in the 90s, they decided to start to cut all these plants. That's called the Work for Water program. But then what to do with all this biomass, with all this waste, rather than just burning it? There is a research group under the lead of Stephen Lamb at the Department of Environmental Affairs that basically developed a concrete, a super lightweight concrete, a blast-proof concrete, a fire-safe concrete that uses, instead of sand and gravel, uses shredded bio-waste, basically. So these non-indigenous toxic plants in the context of Africa as aggregates and for the concrete. So they have been developing this. I'll skip this quickly. But what we are now doing is that they approach us for two ways. By getting the geometry right, they can reduce the amount of cement. By getting the geometry right, they can reduce the amount of reinforcement steel. Both of those components are highly polluting, but more importantly, because they're developing solutions for dignified housing for the lowest income people, what's important there is that that also allows to significantly reduce the cost of these constructions. And we want to try to get all the steel out, or almost all the steel out, and we do this by reintroducing really these Gothic or even Roman ideas of adding buttress walls. So this is the structural principle. So we do have one very efficient deep transfer wall in mildly reinforced concrete, but all the rest of the structure is unreinforced. So we have a very efficient stiffened funicular plate. Then we have all these unreinforced kind of buttresses that are being used for architectural reasons as well. And so we're developing with them, with also the Department of Housing, how we can translate these ideas. What's maybe nice is that for the formwork of these systems, we use with local basket weavers, so local crafts. These people have as only outlook to make baskets for mainly actually for tourists. So now these local craftspeople are activated to make high quality, very unique kind of formworks for these structures. But what's pretty neat is that they weave these formworks using these same non-indigenous plants and bushes and so on. So after use of the formwork, after a few times, so you can use these formworks, these mats, a few times, and then after they're just being shredded and they're used as aggregates for the next batch of concrete. So it's a full circular, no waste kind of production process here. And then, of course, we're celebrating and expanding also these opportunities of then playing with these beautiful imprints of the materials, very much as like the beautiful imprints of the bamboo in Philippe Yuan's project, to really celebrate also how this is made with local crafts and local materials and so on. If you have the chance to go to Venice, then please go to Palazzo Mora, where we are showing this project and many of the prototypes that we've built. So for example, now we're building a full scale, so a 5-meter span real structure. But so here you see some initial prototypes where we make these very thin, stiffened floors out of this very unique waste absorbing kind of lightweight concrete indeed. But maybe what's perhaps even cool about this project, smart brick, a brick that could be cast very simply with the same material, an unreinforced brick. And this brick stable during construction, and that it allows any unskilled labor, so here Juni, for example, to be assembled without the need of formwork. So it's geometrically interlocking. It's optimized not to create too much bending capacity. So it basically uses a little bit of cantilever during construction until you build an arch, and then that arch is stable, and so you can progress in very safe kind of ways. These bricks that are now optimized to be repeated in a with very simple molds. So these bricks that I showed you earlier, by the way, were built in South Africa with very simple molds that are made from developable surfaces and so on. This is, of course, this project or this brick is inspired by, again, work by Matthias Rittmann, where he made these nice bricks that had this little piece sticking out so that they serve as support for the next row being assembled. So we want to continue this research in building in stable sections, so to try to take most of the formwork out as well. So Philippe introduced already in the beginning of the presentation that we're building something special in Venice. More specifically, what we're doing is we're building masonry, but using 3D printing. So concrete 3D printing to be more specific. And so here I'll share you a few things that I'll give you some hints. Unfortunately, I cannot disclose the entire project because it will be launched on July 19th, but I'll give you sufficient hints to really clarify why we're doing this project there. So one of the fundamental approaches that we use, this is of course the research of Shajeh Bhushan, head of the Saha Code group, but also PhD student in our research group, is that we look at 3D printing as concrete 3D printing, unreinforced concrete, as basically the analogy to unreinforced masonry indeed. So in a way, you could look at this as scaling up the problem. But of course, in masonry, you can do much more than just stacking, than just corbelling, than just kind of printing horizontal layers. So we also want to basically show that we want, through non-uniform, non-parallel layers, that we want to also be able to activate in arch action these 3D printed layers and to nicely keep them stable so that you don't have delamination issues and so on. In order to achieve this, Shajeh has been developing basically an approach that allows to focus really on what we think matters, and that is the control of the non-uniform print paths. So that basically what we do is we model our geometries such that the print path and the stability of the print path and the alignment of the print path to the force flow, that is what we explicitly encode. So that means that the geometry is implicit. This is fundamentally different than how 3D printing currently is typically done. Geometry is being modeled explicitly, then a slicer is being used to generate print paths, and then this is being printed. So we do it the other way around. We actually use these morphing fields, these distance maps to basically do that. So what's also important is, in order to not have to try and analyze and so on, Shajeh has been focusing on a one-to-one relation between the entire design pipeline and then also the manufacturer, so that all challenges can be caught from the beginning. And then more specifically, he's using these contour maps, these to encode all of these elements. So there's two things. There is the synthesis of the task graph, but also the stability of the task graph. So using functional representation, or as I emphasized, implicit modeling, this allows us to basically make sure that you don't have overlaps that are not sufficient, that you can align to certain kind of prime axis and so on, but that you can also print sophisticated pieces like this. So it's very much with the graphs are representing the main directions, and then these morphing kind of bitmaps allow you basically to also deal with non-continuous topologies in the geometries, which is very important to actually have a very smooth evolution of, for example, the infill in your elements, but which then also allows you to generate these elements that were, by the way, printed in one go by changing direction with the robotic 3D printing. So here an example of what I said, with very different morphing typologies that are being projected along non-straight kind of elements. So this is, we're not talking about the typical extrusion-based 3D printing that everyone is doing today, but this is a two-component, more sophisticated robotic printing that then, of course, allows us also to have this more controlled kind of evolution of profiles and so on. Why I'm showing a little bit of a background of Shajie's research is because this is, of course, one of the fundamental stones together with our research on masonry mechanics, so the research of Alessandro, for example. We brought all of this together to make a bridge, a 3D printed bridge without reinforcement, dry assembled and so on for the city of Venice. So these are, of course, the important references. The armadillo was important. The advances in concrete 3D printing is important. And so we decided, can we make a 3D printed a masonry bridge, unreinforced masonry, where every single element is 3D printed with the print paths and the layers aligned to the dominant force flow. So this was the teaser video that we sent out a couple of weeks ago, because due to all kinds of issues that we have encountered, we didn't, unfortunately, make the opening of the Biennale. But this project is too important to us to make shortcuts. So we decided to take it forward, how it needed to go forward. And so we developed the entire pipeline. And we really want to demonstrate that such an integrated computational design approach allows you to actually offer, in a way, absolutely a new language for concrete, a concrete that is very precisely placed, that is fabrication aligned, that is structurally informed, that is unreinforced, so that it can be easily recycled, that can be taken apart, so that it can be reinstalled somewhere else, and. So this is a collaboration between ETH, my research group, and Zayadit Architects. So let's quickly go back to here. But then also a very important partner is Incremental 3D, amazing 3D printing boutique startup out of Innsbruck, and then with the large support of Holcim, who also provided a unique two-component print. So here's some more hints of what's going on. So we developed a framework that allowed to basically iterate and to optimize all these different competing parameters, print path, length, when do you reprint on the same elements, how do you very smoothly morph, what is the allowed overhang, what is the weight of the component, how to install it. All of this is encoded into the computational pipeline. And here you see some printing of this non-uniform printing. Do notice that the head of the printer is hidden, because this is we were not allowed to share. But you see quite sophisticated, non-uniform, 3D printed kind of elements. So here then a few glimpses. Again, I'm actually not allowed to show this because it's not open yet. But for this audience, I thought I had to share a few images. Very important is to have very good footings, because otherwise you cannot do this as an unreinforced masonry. So we have steel footings, reusable footings that are connected with tension ties. This is always cool in Venice, that everything needs to arrive in these barges. So all these components arrived. We attached the tension ties, and then this large span. So from corner to corner, which is the effective large span, we have over 20 meters of span indeed. So here you see some of these elements. I hope you will be able to visit, because the quality of the concrete print is just absolutely ridiculous. I cannot believe, sometimes you think you're looking at aluminum. It's so neatly kind of all these little layers. So you see this also here during construction. Beautiful alignment to the force flow. I'm clicking a bit fast because I'm giving you a scoop that I will not show you the final structure. But the key thing, what we wanted to address here, is that we believe that you will hit new efficiencies of using concrete, so new sustainability targets, if you adopt a new language for concrete indeed. So this striatus bridge is dry assembled. That means that you can take it apart, you can reuse all components. It is fully unreinforced, which is important, together with all materials are entirely separated. So we don't mix materials, we don't embed reinforcement, we don't glue things, we don't add kind of additional things that could pollute the material. So that means that the combination of fully unreinforced and separated materials makes it low energy recyclable, which is a big advantage of concrete, that you don't lose quality when you recycle. Low stresses, which means that now the ink is maybe still a little bit on the polluting side, but because of the low stresses, we are giving the challenge to material scientists to actually go for printable materials that have low impact, like you saw Benjamin Dillenberger doing with Guillaume Aber, directly 3D printing of construction waste. Why I mentioned 3D concrete printed, what is important there, most people focus on the formworks, but I also focus on the reduction of internal materials. So because what we need is the structural depth, but we don't need this as a solid section. So through concrete 3D printing, we can achieve this structural depth. And then again, being force-aligned print paths is essential in order to guarantee that you don't delaminate. And I should have added this picture. If you take one of these bricks, not how it wants to be loaded in compression, then you actually immediately take the laminas apart, right? So it's super important to do that, because otherwise you will have to cast high strength concrete into this, or you need to post tension this, or a combination of all the rest. So we want to show a pure way of using concrete, the artificial stone that it is, right? So here, another sneak preview in the back. So it will be opened the 19th of July. Go check it out. I couldn't believe my eyes when I saw it, the finishes. I hope you will enjoy it as well. But as in all our work, we are not doing anything new. We're just reintroducing common sense. This is maybe the historical striatus. You see that these masons, of course, placed the bricks where they needed to be. So the notion already that we would just have a layered kind of section, the master builders of the past would be making fun of us. They would not understand what we're doing. So this is what we want to demonstrate with this project. As a last call, I want to say it's important that we work together. It's important that we share our innovations and so on. So maybe have a look at Compass, because on Compass, we are sharing all our algorithms, all our methods for you to try to do, to reuse and to do what we do indeed. So I talked about structural geometry, so shells, vaults, and so on, to reduce the volume. I emphasized multiple times that that is not enough. It's not just about the volume of materials. We need to use lesser polluting materials, and that will only work when the stresses in the material are reduced, and that is where we activate compression form, so funicular form. Through computational fabrication, again, computational, the emphasis is on not just using kind of machines, but actually understand the opportunities, the limitations, and the challenges of machines. That allows us to really reduce the waste. But all of this needs to come together, and we are being challenged by very inefficient systems that have been optimized for decades. When it comes to cost, so for example, the flat floor plates with simple reusable formworks, it is so efficient that we need to find a way to challenge the economics of all our innovations. And I'm convinced that you can only do that by having an approach that considers all relevant aspects. So not just design and engineering, but also mechanical systems, also how it's fabricated, and last but not least, how do you then install all of this on site? If you, by taking all of this into account, I really believe that we can challenge also the cost of these elements. And that is exactly what we're doing in this project that I showed in Brussels, where we are using these floors in a real high rise. We are actually at the same cost level as a hollow core optimized prefabricated system, right? So this is what we need to achieve, but we can only do this by working together. And we believe an effective way to work together is to use computation. So with that, I hope that I gave you a lot of material now to open the floor for a discussion, for questions, for all kinds of things, because if anything is not clear, if you're skeptical, if something needs to be clarified, I'm very happy to answer any questions or comments that come up. But in the meanwhile, thanks a lot for your attention. And again, Philippe, Neil, thanks a lot for this invitation.
Thank you so much. Really mind-blowing, especially the last project. It's really high quality of to 3D concrete printing, such a 100% compression only concrete bridge with no digging foundation. Actually, it's just putting on the ground. So that's impressive. The quality is very high, and also we can see if you have done any robotic fabrication before, the details really matters. So actually, the concrete printing is really difficult because of the material and need to be very difficult to control the quality and stable, because you should print for a long time, and the quality of printing always a big challenge to different research teams and different companies. So we can see the European style to doing very high quality technology because it's like a global competition in concrete printing. I think more than 100 teams right now doing that work, but this one is really, really impressive. I think.
Thanks, Philippe. Can I maybe immediately make some comments to this, because I want to clarify two things. One thing is that I think if I didn't emphasize it sufficiently, then I need to repeat myself, is that the quality of the printing also comes, of course, by working together with Incremental 3D. We have been collaborating with them, so particularly Shage, for many, many years. They have been perfecting their setup. And that is something that we also need to really acknowledge, this digital crafts, this craftsmanship of these new robotic processes. And so this didn't happen overnight. So we have been working with them for years and years until now we saw, okay, we're confident enough to do something like this, right? So that is maybe the first point that I want to make there. And actually maybe an interesting insight, these guys at Incremental 3D, they were students of Patrick Schumacher in Innsbruck. So they're architects. They're people that understand the sensitivities of the details that matter. They also understand to go the extra mile and not just crank out in a brute force and trying to make money. So that's something that we really need to acknowledge. Another thing that I wanted to say is that, yes, a lot of people are 3D printing, but almost everyone is using what is called the 1K mix. So these are 3D printers that optimize the length of the pumping and then at a continuous rate kind of squirt out a mix that is just stable enough to print and so on. What we are using, and I also want to make that distinction, is what is called a 2K mix, where basically at the head, at the robotic head, the concrete, the retarded concrete, and then the anti-retarded are mixed exactly when it comes out. And that allows much more precision and kind of non-uniform kind of placing. And what I wanted to say is that there is maybe a value to the brute force, large scale. Many people are also starting to suggest to go on site with big gantries and directly 3D print your house and so on. Okay, fine. What we want to demonstrate is that if you do have the quality or the control of non-uniform printing, then I think we are starting to use concrete how it wants to be used. In walls, it wants to be used horizontally, but anything else, and I made kind of an argument that spanning space is the most inefficient kind of and problematic aspect in construction. And that is where arch action really could offer some opportunities, right? And then, great. Yeah, okay. So maybe just to react directly to what you say.
I think because we are doing the similar research and not only design, but also we're doing the fabrication development by my team. So I totally understand the difficulty, especially the quality of printing is really difficult. If you want to improve a little bit, it's really a big challenge. So I think you're mentioning the ways how you integrate two material together in the factor. That is actually the similar decision we made from last year, because we're testing the similar things. And the quality of our printing is, we can compete with yours, but maybe still have some small distance. We need to.
Again, it's not my printing. It's not my printing. I cannot take any credit.
I just feel it's really impressive for the printing company. At the same time, I just want to congrats your student, Xiaojie, your PhD candidates. He actually really doing something very important, because the two-pass planning based on different geometry, and especially which the challenge because continuous printing need to taking this different kind of joints. The joints is compression only, and the geometry two-pass planning is extremely difficult. But I see some part of it very quick of your details. I think Xiaojie really do a meaningful research. I think that's a research, because the geometry system, the geometry, parametric geometry have quite different to the fabrication geometry. And also the parameters should be redesigned a lot of times, and also control the printing speed when you're turning some corner, and if you want to cantilever for a little bit, it's really a big challenge to keep the quality at the same time. So I think it's a great collaboration between your team and the printing company. It should be not difficult. Sometimes the success will really a lot of things behind it. So we can see the quality and the work. Great.
Actually, it's even now after the process, we are having so much trouble. How can we clarify how many loops, how many connections, how many dependencies, how we really approach this project, right? Because it's by just presenting it in a matter of fact, as we do, as I tend to do, these dependencies and connections, because this is many teams in many locations working together on this, right? And so that's kind of also, it's going to be challenging to try to clarify this. And I don't want to celebrate it, but I want to clarify really what I mean when I present, I think an integrated computational process is needed. And so we'll see. I mean, we still have work to get our presentation ready.
Your presentation in July, I think we want to see the final object. So what it looks like without scaffolding and very clean in the environment. We're looking forward for that. It's almost finished, but you keep a secret, right?
I have to. I mean, I have to. There's partners behind this that I would get in trouble. I would really get in trouble if I show you how it looks now.
Okay, I think maybe I put forward a question, and we have a lot of questions followed. I think most of your in most part of your lecture, you still mention a lot to the environment friendly vision for the future digital fabrication research. I think that's really a big challenge, especially from last year in my country, in China, the central government president put forward the low carbon strategy as a whole country strategy for the future. So I think it's very impressive for your research, because you already make research on this for a long time. Especially, I think most of them put our attention in the energy resources and in the operation and the management process of architecture, but we are designers. So the design and the construction process actually really matters. The efficiency of the building for the future. So it's really clear for we can very strongly impression from your presentation. You give a very clear framework of your vision, especially you focus on the floor, that is 40% part of the buildings. I think it's really impressive to change the flat slabs to some like optimize slabs in the future. So that's really, yeah.
Yeah, can I maybe add to this, because and I try to weave it in, but maybe I didn't hit the different layers that I recently, and also through working, for example, in this project in Brussels, we because there's all kinds of also now sustainability consultants that really hammer you down, and there's targets that need to be reached by clients, and so recently we have been learning about a lot more that it's really also not about the embodied emissions. It's also about opportunities of research about, and this is the big challenging one. The next one is to keep materials separated so that that these materials become building stock or kind of usable in the future. And so can you actually do what you do? But additionally, can you give yourself the challenge to actually connect everything mechanically so that it can be taken apart rather than chemically so that it's embedded, glued? Because as soon as you start to do this, and another example, I talked a little bit about timber, that timber is not guaranteed a green solution. And one of these challenges also about timber is that if you need to go to engineered timber and you go to glue lamps and all kinds of, you start to glue the timber, what you're also doing is you're somehow also locking in the use of that timber. And so in the end of life reuse and so on, it might also be challenging. Other things also, like for example, in this high-rise project, in order to achieve certain standards, also the building performance needs to hit certain kind of efficiencies. And in order not to have like crazy air conditioning or ventilation kind of systems in there, they also want to use the thermal mass of the building. So the concrete floors and the rest also to have this kind of moderation, short-term kind of moderation over 24 hours that happens in the first 5 centimeters, and long-term heating and cooling storage to be kind of to even out kind of the peaks over longer terms and things like that. Why I say that is because, and I was surprised, I learned about all these things, is that is why the timber floors almost immediately got discarded for 2 reasons. They didn't have thermal mass that could be activated, and that was essential to significantly optimize the operation of the building. And secondly, they are lightweight and they needed a lot of sand and additional materials to be acoustically performant. And so to me, this was actually a big surprise, because I thought that our #1 competitor when it came to sustainability targets would have been timber. But actually, with all the extra measures you need to do to make timber feasible in a high rise in Brussels, timber was actually immediately excluded. And so to me, all of this is our new insights that I think are super exciting. And again, I say these things not because I want to lobby for concrete or anything like that. Absolutely not. What I want to say is that we need a much more nuanced understanding of sustainability, and we also need strategies to calculate the bigger picture. So now people focus on this material versus this material, and that is wrong. We need to calculate a system, a building, a context, end of life scenarios, and. And again, I think that is where, I mean, beyond digital fabrication, where really computation, modeling, learning also from experiences, to kind of talk to Neil through AI, and learning and accumulating more and more data so that your decision making is more informed in the beginning. I think that is absolutely something that we need to do better. And I think our field, our community has a big advantage, because we have the tools to bring all this scenario thinking, this kind of long-term kind of experience in there.
Yeah. I think it's great for you to set up a certain kind of connection between this kind of sustainable thinking to the design process. Actually, computational design is a bridge, I think, which actually make connection from this kind of multi-objective design directions, and transfer this kind of design thinking to control the whole process, not only in the form, but also in the construction process. So that's the meaningful things for the whole community. I think we really appreciate what's your research and the contribution, especially very, although you're both structural engineer and architects, I think it's really cross-discipline connection, integration for the knowledge, the new knowledge in the future in our industry. So Neil, would you like to add something?
Yeah, thank you, Philippe. It was a fantastic lecture as always. I guess I was struck by one thing. There's kind of like there were these two kind of opposing forces which were kind of going on in some way. The kind of like the sharing of information. I thought your GitHub thing, that's an incredibly generous gesture of sharing information, and then the kind of the other side, which is to say the competition side of things. I mean, it's always a challenge when you're working internationally. To operate in a way where you're completely democratic and you're, but at the same time you're at the risk of other individuals not partaking in that kind of global community. For example, Trump pulling out of the Paris Accord. How do you work internationally when there are these other people who are operating in a more kind of fascistic way? It's a challenge, and I think when it comes to the kind of the knowledge transfer. I mean, I know that having worked with Berokos Neves early on, and he of course copyrighted the contour crafting spatula logic. Which is in a way unfair because it means that nobody else can use that. Although it seems that now these new developments that we don't need it so much. I mean, it seems that actually that the detailing is so precise. Who cares about having a spatula to smooth things out? But then we weren't able to see the kind of the photograph of the nozzle itself, and the nozzle is absolutely crucial. I know that Berok has spent years working on the nozzle. That is almost the most important part of it. There are lots of challenges with printing concrete, but you're getting a situation whereby some information is held and others is shared, and that's the tension in some senses. Like, I think within the kind of research community as a whole, one thing that we've noticed is that the kind of non-disclosure agreements, are kind of blocking the sharing of knowledge, which is an unfortunate situation. It was very generous of you to kind of to show us that work. I mean, beautiful work in Venice, but I mean, had you been strict to various things, you should perhaps have shown it. But anyway, that seems to me the interesting kind of tension of how do we share knowledge when we're also confronted with this kind of competition where it's the sharing is precluded.
No, I mean, thanks for that comment. First, thanks for the nice feedback, Neil. But also, I really like your comment because you cannot believe how much stress this causes in our daily life. This continuous kind of treading carefully on what are we allowed to do. So, for example, the project I brushed over it a bit, but I'm super excited about what we call this click brick that we developed in a South African context. And so there were two strategies there, right? We could have tried to go for a patent and so on. What we did is, no, let's show it in an international exhibition. Let's write our papers about it so that people can really use it, right? So this is because we really want to, we think it makes sense, and we worked it out. We used all our privilege, all our computational methods, all our kind of research history to get now to a super dumb one element that does something amazing. But this has all this. So we said like, okay, let's just like, I mean, we have thought of it, right? We thought like, no, we need to patent this. This could make us rich. And then we said like, this goes against everything that we believe. But where we do want to be careful is, for example, in the development of the floors. If I were now to share everything too openly, then we take away all our chances to really interest a large partner that could help us scale this, translate this, and scale this up to a size that really starts to matter, right? So, because if we now too freely share this, then it's kind of a nice demonstrator, it's a nice prototype, it's a nice but that is actually a situation where we are being more careful because we do notice and understand that industry partners need to have a unique hook that cannot just be overrun by competition indeed, right? And so that is actually me being very pragmatic and also much more real, that there, because of the potential gigantic impact, we all need floors, that one I want to be a bit more careful, because I think it needs to be able to be translated at a large scale. So imagine half of the world, a third, a quarter of the world being built with these kind of systems. That would really change things. That would really kind of cause this dramatic reduction in resources and so on. And that is where I do need to play the game. That is where I do need to actually give our industry partners sufficient ammunition, safety, IP protection, that it's for them justifiable to put a lot of resources towards it, right? So in that sense, yes, there is 100% attention, but there also, I think actually something else is that if you go to Compass, if you read our papers, if you read all these things, then you could say, actually, we can redo all of this. I mean, it's not, I keep saying what we propose is not rocket science. It's just taking advantage of computational methods to reintroduce. And then Tom, with whom I co-lead the group, Tom van Melen, we met last time when we were all together. Tom says, like, actually, it's not rocket science, because it is rocket science, because what it actually demands is having sufficient experience, confidence, and also the tools to actually trust these historic principles that no longer appear in model building codes and so on. So actually, that's also an interesting tension, is that actually the tension between common sense and then the reality of suddenly you're confronted with, if I use my common sense, then I cannot fall back on building codes and things like that. So you have to take that leap. And sorry, I'm mixing all kinds of things, but yeah, it's quite interesting trying to have that balance between what do we want to share everything. I mean, believe me, we are doing this. We have a privileged situation as academics at an institution that gives us all this support. So we want to give this back. The few times where we don't immediately give it back is because we have the feeling that we have something big that needs to be be Yeah, anyway. I hope that makes sense. I mean, so I hope I'm not contradicting myself. It's just
absolutely no. It's a difficult. I mean, people are always very kind of conscious of not being copied and so on and thing. But actually, the ideal thing is to be copied everywhere. I mean, if everybody adopted your work, then you would really have an impact on the world. But I guess it becomes a huge question when we're all seem to be interdependent in some way. I mean, the whole thing about the energy and so on, greenhouse emissions and so on, is important. Equally, COVID, the fact that certain countries have all the kind of the resources to deal with it and others don't, well, that means that COVID spreads around and actually affects the international community. So it is a very interesting tension that you're doing. But I want to just thank you for sharing your ideas and be so generous in the way that you have been. So it's a very important gesture to make, and that's something at the heart of what we're trying to do to overcome the other historically important things that have been bequeathed to us. So thank you.
Yeah, thanks for the comments.
I think some comments to Neil's question. I think Philippe Rock is famous because of the very open source platform Rhino Vault, because all the students, this plugin is really famous in Rhino software. I think it's an open platform for a lot of users, especially for the young designers, students. That is a way open his research. I think Philippe Rock have some very special character. On the one hand, he's extremely strong in the graphic static study. That is a fundamental knowledge, actually very, very important, but actually a lot of universities just skip it because of the new digital tools. Goes directly to the very complicated analysis, but actually the graphic statics is so important to review the essential, the force flowing, or actually the force. You mentioned the strength from the forces. That's extremely important, because after collaborating on and learning from Philippe Rock's teaching, I think he's strong because of his fundamental knowledge, and his fundamental research is really very strong. On the other hand, I think he is doing something meaningful although he still keeps some secret in his research process. But I think right now the most important is Compass. I think Compass is very interesting platform because that Python is a kind of language you can open source all your research process to the other partners or other researchers, and standing on the giant people's shoulder and making something interesting. So that's a very good idea. 5 years ago, when I talked to 3 or 4 years ago, I talked to Philippe, but they are really doing this quite well. We frequently go to see what's happening in Compass. I think you make a really great progress. Different teams collaborate very well on this platform. But at the same time, it's still difficult because it's not just easy open Python. You can just make use part of it as a library to develop a certain kind of different motivation in your research. I think that's a culture in GitHub, because GitHub gave a really big platform for people sharing their open source scriptings there. But still, right now, it's not just software. We have a lot of hardwares, and it's kind of integration from software, hardware. And the fundamental knowledge in architecture is not just about AI and about form making, which sometimes the whole process is so complicated. Not only the material process, but also the proving process. I think the calculating is not just about form. It's about safety and about the regulation, the code, a lot of things. So it's not easy just implement one tools in even just a formation. Sometimes we need to change different platform and coding different codes and develop our own toolbox. So I think the future culture is kind of integration and learning from each other. So this kind of open source culture is extremely important. So I think Compass is very interesting. I want to ask Philippe, would you like to give more detailed framework introduction of Compass, and what's your future plan on this platform in the next 1 or 2 years? Because from a global perspective, that is the most impressive part for NCCR right now. So we want to understand what's your vision and what would you contribute to the world from this platform, because you're a director, you are the boss of the platform, right?
Yeah. Well, actually, Philippe, I think it would be great to maybe also for one of these events, maybe invite Tom once, because the mastermind behind Compass is Tom van Meulen.
Yeah.
And it might be a great opportunity for Compass, but also I think for this community to get an updated kind of a state of the art of what we're doing, why we're doing, but also perhaps more importantly is the mechanisms behind it. And so the safety mechanisms, the community mechanisms, the open source kind of strategies, but also the rigor behind actually everything that is implemented and how it needs to be documented and so on and so on. So for me, I mean, I'll just make a few kind of bold statements, I guess, because you're kind of asking for it. How we use Compass, and that is, of course, I mean, Tom developed Compass, so it's an in-house kind of tool, but it really allows us to, in a super lightweight formats and data exchanges and so on, to never have any clashes, to never have any kind of material loss, to go well beyond a BIM kind of logic. So we also use obviously BIM, but we do it differently. BIM for us doesn't mean the super constraining IFC format that is imposed by Revit in a Revit software and things like that. And so basically what it allows us, it allows us to rethink how we collaborate together. So like also, for example, for the bridge, you only need to then care about the interfaces between all of your you just need to quickly set this up. You need to agree on this, and then all your teams can in parallel work on the same project. So without any kind of clashing and so on. And this to me is really the future, because I think it's for all the impact that we have with what we build, how crazy is it that we have to have these super tight deadlines? Because if we don't do the design by then the engineers cannot do it by then, and they cannot then give it to the contractor. If all of these people can start thinking at the same time, developing complementary kind of logics, refine the understanding, the design goes together with the development of efficient details, goes together with the iterations of the engineering in parallel, and so on, then I really think that we can get to other kind of benefits. So to me, something like Compass, maybe it will be Compass, but an attitude like Compass could really be this integrated project delivery model of the future. And particularly, that's also what we need for digital fabrication, to really start to capitalize on it. But actually, I want to share something very personal, because lately with we through the NCCR, Compass is being presented, but actually Compass is not an NCCR project. It was a 100% BRG project until maybe a year ago. Its Compass core was translated into or transferred into a community project, right? Which still Tom as main developer, but now it's a community project. And why I say that is because we have so many reviews, and it's crazy how much resistance you get, because what we are doing, and I recognize this exactly. When I was a young professor starting, then I wanted to write my papers about the new methods that I developed. For example, TNA, what is behind Rhino Vault. I wrote papers, I wanted to write papers about masonry assessment and so on, but I didn't manage to publish anything. So this is maybe interesting to young researchers. I had no credibility. Everyone was always rejecting. There was skepticism everywhere. Why was this happening? And I recognize something very, very similar right now, is because what I was proposing with TNA for the assessment of masonry was breaking with all the old school kind of outdated models that people built their entire career on, right? And now I am noticing the same, that we get so much critique, skepticism from people from industry, from people that tried 20 years ago to develop something similarly, but the world has changed. That this same vision didn't work 20 years ago doesn't mean that we will also fail. So you cannot believe how much skepticism there is from people that have built their entire career on basically something that we are now saying, this is really not the way to do it. This is not how we will solve this huge challenge that we have, this environmental kind of pressure, all these expectations, and so on and so on. So, I mean, this is totally not relevant, but I thought maybe I'll share something personal, that currently we just have to do it. So actually, we're no longer trying to present it. We're no longer trying to publish it. We're no longer, I'm having exactly the same attitude as 10 years ago as starting professor, because I know fundamentally that we are on a relevant track. And actually the academic environment, but also the environment of frustrated or whatever it is, kind of professionals, it holds you down. And so let's see if this will work out, right? So, but we are on a mission. We are lucky that I'm tenured, so I don't need to publish anymore and so on. We will just keep pushing Compass because through increasing kind of also experiences in practice, we feel that this is the way forward, right? And again, with that, I don't want to say that Compass is the holy grail, but for sure the approach, the concept and everything, how we approach it might be an important strategy. And I'm preaching to the choir because you believe in very much the same things, Philippe, and you also approach it in a similar way. So I have the feeling that we need to keep pushing. But what is a little bit sad about what I'm saying now is that, and that's actually perhaps relevant in the context of I like the term inclusive futures and so on, is basically that also this academic this academic business where in certain countries it's really not even about quality, but it's about how many papers you cranked out that week even, right? And about silly factors and indexes and so on. If your code is being scrutinized and valued and kind of looked by an online open source community of 2 million people, and they say, great job, I think that is more relevant than a frustrated academic in a double or in a single blind, even worse, in a single blind kind of review process, that because you're encroaching on a field that is no longer relevant, but you're commenting on it, that you're being held back. And so that's what I like about everything that you guys are doing. This inclusive futures is super important because we need to also start to create kind of an environment where we find other mechanisms than the outdated ones to actually disseminate, one, but also to value quality and value impact and value knowledge transfer and so on and so on. And so anyway, just to say that that is also why I'm always super thankful when you invite me, because this is a super important organization and community.
Appreciate sharing the same vision with us. I think that's why we invite you, invite like Mike Share and invite this one Archimedes, maybe not because you have very big, important, most important paper, but because we can really learning some fundamental knowledge from you and learning the process, the experimental things you are doing in the whole life. I think that's much important than the publication, right? So
well, let's really Philippe, let's be clear though. By the way, Mike Shea has one of the most important papers and results. He's the founder of BESO, right? So I mean, it's I see. Should we maybe address some of the questions that we see in the chat, or I also see that Cora raised her hand.
Yes.
Maybe we can go to Cora.
Yeah, I think they have a question here. Great presentation, Professor. There were many 3D concrete printing architecture in China, Europe, but it is not used widely. What is your vision of 3D concrete printing in the future?
Yeah, so I tried to argue in my lecture that I believe that we need to really be skeptical, critical. We need to fully evaluate what a certain material does best and also what type of fabrication processes do best. So for example, if you use concrete 3D printing to make a more sophisticated stay-in-place mold for something else, then I question if that is really the most valuable thing forward. If you use concrete printing to build very fast foundations or walls with very low impact materials in a logic that makes sense to go linear high, then I think you're already doing better. What I try to show is that if you really want to activate concrete, not just for the banal application of a vertical wall, but you also want to span space, which really is the bottleneck actually. Can we develop systems to span space, so to walk on, to make floors and so on? Then I think, I believe that there is an opportunity for force-aligned concrete 3D printing that allows actually to do bespoke, sophisticated, unreinforced kind of concretes and things like that. So why is it not widely used? Well, I think exactly because of that. Is all, not all, sorry, this sounds so horribly judgmental, but are all of these, are really all is all this 3D printing really what we are needing? Is it really needed? What is it solving? What are we really trying to do beyond the fascination and the kind of not properly argued kind of thing like, yeah, but you place material only where it's needed. Yeah, who cares if this material is super polluting? Who cares if the process is super, super expensive? Who cares and so on? So I think concrete 3D printing will suddenly become relevant. If it becomes relevant, if we find exactly an area where it will really contribute something that we're lacking, right? And currently that is not the case yet. currently, in most of the concrete 3D printing, it's still a bit stuck, in my opinion, with fascination, trying to do, if you see also all these concrete printed houses, they look like regular, even extremely badly designed houses. So something that already gives me a hint that that is most likely not what we want to do with concrete printing. I'm always skeptical that when you see the things coming out of a totally disruptively different kind of fabrication process, if that looks exactly the same as what you did before, then probably you're not fully using the material what it's used for. So I think why it's not widely used beyond kind of limitations of codes and norms and unknowns of the material and so on, I think it's because this technology is really not yet used for its high potential. So sorry, that's a bit vague, it's a bit abstract, but I think it's true what we are showing with the bridge in Venice. I'm trying to give maybe a hint in what direction I believe it could go. Not should. I'm not convinced yet that concrete 3D printing will ever be relevant, but at least we're showing a potential hint. Let's see.
Yeah.
Philippe,
Yeah,
can I just
another
draw
question.
attention to a few things in the chat? There's from YouTube. There's someone called El Curvo. I don't know what that is. The workshops that you're given are closed, but is it possible to participate, at least to attend by watching? Will you be live streamed? We're trying to make everything live streaming available for everyone without registration, so they can all watch.
Okay. Yeah, sure. I don't know. I guess this is fine. Maybe we should ask this to my specific team who's doing it. I think it was also streamed last time. The only thing which is a little bit of a challenge, of course, is that we do have to restrain the group to a manageable size to kind of be able to deal with the questions and the follow-up and so on. So, but yeah, I expect that it will be streamed like last time.
Yeah, not this. I think live streaming they can't ask questions and things, but
yeah,
anyway,
that's a pity, of course. Yeah.
Yeah. So there are a few other questions in the chat. Hold on a second, let's find this one here. Arturo Gutierrez, great lecture. I'd like to ask you about concrete optimization in seismic contexts. He's from Peru. How can you face the seismic parameter with sustainable digital construction?
Yeah. No, of course. I mean, so again, each time that I get this question after my lectures, I should make this clear, right? So building entirely unreinforced with weak materials, of course, works for certain areas. Like you would not build anymore an unreinforced masonry structure in San Francisco, in Chile, in Turkey, and so on. So it does need to be appropriate. So we do look at things like seismic. And in fact, what I didn't say, because it's a detail, but maybe it's an interesting detail, is that between all the different discrete elements, we actually put some simple neoprene pads. These neoprene pads, actually, they do different things. They distribute the stresses at the interfaces. They actually provide a very precise and controllable friction interface. And then actually, to the question of Arturo, they actually also, if you would have a seismic event, then the structure could rock. And basically, all these interfaces between all these discrete elements, they dissipate the energy. So what we do actually in discrete elements, masonry systems, the ductility doesn't come from a typical ductility of the steel, but it comes from the capacity of the structure to move. It comes from the capacity of the structure to disseminate energy in between the elements, and so on and so on. So it's a different way of actually looking at seismicity. That said, the specific bridge that we built in Venice is built for a Venice, Swiss, that kind of context, right? So one would need to be a little bit more careful when one designs in these ways in a heavy seismic zone, right? So, but in a way, there is nothing that prevents this. And I want to maybe answer another kind of question, answer there. If you look at, for example, Mexico City, there was this gigantic earthquake in the 80s, and many structures collapsed, and the beautiful, extremely thin structures by Felix Candela, but also the unreinforced brick vaults in Mexican vaulting survived these earthquakes. And that has something to do with the the capacity of good structural geometry to take a lot of different loading cases, but also these structures are proportionally so light, and their resonance frequencies are not even being caught by these seismic events. And I'm not precisely answering your question, but I'm saying that there is outlooks, but of course, like you want to be aware of what materials or solutions or crafts you can use locally, you also obviously need to be aware of other conditions you need to consider. So, but thanks for that question, because I should be more explicit about these things indeed, that not everything I present can be literally one-to-one translated into every context, right? And certainly not in high seismic kind of context. Yeah.
There's another question in the chat from Syed Mobin Musavi, I assume from Iran. Intriguing presentation and work. I would like to ask more explanation about the design considerations in the interlocking connection between the components.
Yep. So I assume you're referring then to the project in South Africa or the project by Matthias. So there actually, what's interesting there is what we're doing is the most relevant load case is of course the final geometry and all the loading cases that it needs to take. But what we're trying there to do is, can we actually design interlocking features? In fact, they're not interlocking, by the way. They're just cantilevering. They're kind of like balancing features more than interlocking, that actually don't cause extremely concentrated stress accumulations. And so basically we're trying to work with the interfaces and the geometries such that actually you can temporarily cantilever until you form an arch. So that is of course important, right? That we are not over-dimensioning these elements. They have only a very temporal kind of function. They need to be just strong enough until the next stable arch that nicely keeps it together is being formed, right? And so this is kind of a continuous back and forth. And to be more specific, to answer your question more specifically, we do this with a loop where we basically optimize the final geometry to be not only funicular but also stable under any loading case that it's expected in the final structure. Then we discretize it, and we test every single discretization using discrete element modeling, or a technique that an open source discrete model that we use, which is called rigid block equilibrium, which you can find on Compass, by the way. And we use this to understand the in-between stability and balancing of these elements. From this analysis, we get all the contact forces between the elements, and then we have a last step where we use finite element analysis to actually understand the full stress, contacts, and distribution within the elements. So basically, we loop many different tools. So an equilibrium tool to find the global geometry, discrete element modeling, or a rigid block equilibrium modeling to have local balancing and reaction forces at interfaces. And then we refine it to make sure that at no point we basically exceed stress limitations, because we want to use low strength, low pollution kind of materials. So we built kind of a loop around all of these things. Yeah. Actually, thanks for your question, because this maybe shows a little bit that what I'm talking about, and maybe I should include this a little bit more explicitly again in my presentation, just having the funicular or just having a hanging kangaroo model, that is not where the design ends, right? There is much more that comes into all of this. So thanks for that question.
I mean, just to comment, the follow-up question in the chat from Arturo, Gutierrez, who's in Peru, he said, oh, by the way, we had a 6.0 Richter scale earthquake last night. So I guess we also get to see how many people from all over the world are listening. It's really astonishing.
Yeah. Well, I don't know. I'll have to ask with my team, but I think 6.0 it would be able to take, I think, but we'll have to check it. In fact, for the papers, we will do some more analysis. I would be curious to see, but 6.0 still should be manageable, but I'm not going to promise it. But thanks, Arturo. I'm sorry that you have so many earthquakes. Yeah.
We have them every day in LA, literally. There are about several every day. But
Oh, yeah?
that's when you wake up and notice. But,
Okay, I think it's a great talking session between the audience and the floor to Philippe Rock. It's a great honor to have Philippe Rock here. And 2 or 3 days later, we'll start the joint workshop with Philippe. And still a small bridge, not bigger, not as big as in Venice, but it's still meaningful for a demo between Rock's team and my office. It's like a small demo for the future. So we're looking forward to have Philippe in the workshop. And thank you a lot for your great lecture, and amazing project is happening as always. So we're looking forward to see your pavilion in Venice very soon for the final performance of your project in the opening of Venice Biennale. So thank you a lot for your lecture. So Neil, would you like to end today's lecture?
Just to say that when we speculated on the possibility of what we could do with this platform, we were thinking, well, this whole pandemic thing has forced us to rethink everything. And one of the things is just the basic logic of education itself. The idea in the past that we had all these single professors and single classrooms talking to a single group of students doesn't make sense anymore. And, to be able to kind of democratize that platform and allow some of the, really the key thinkers in the world, the leading thinkers in the world in the last few days. I mean, incredible. Akim and Roland, yourself, and Jenny Sabin and Areti has been absolutely phenomenal. And I think this is actually a revolution that hopefully we can push further, because the knowledge we believe fundamentally that education should be a human right, and it shouldn't be a province of the wealthy. So thank you so much for sharing your knowledge today. Inspirational work. I mean, absolutely exquisite work. Anyway, beautiful. And I always, whenever you show King's College Chapel in Cambridge, that always warms my heart, because that's what inspired me to do architecture in the first place. So, and I studied at Cambridge because of that. But thank you so much. It was a beautiful, beautiful presentation as ever.
Thanks again, and thanks also for these nice words, and keep inviting me. I mean, as I emphasized earlier, I feel fortunate to be part of this. And I look forward to keep collaborating, and also to seeing you live sooner rather than later. We miss each other, no? We missed the nice evenings together. So thanks again. Thanks everyone for joining. Thank you also for the very nice comments in the chat and on YouTube and so on. And looking forward to seeing you soon. But for now, ciao.
Oh,
bye everyone.
Bye.